There is a number that sits at the very edge of physics, and almost no one outside a handful of laboratories has ever heard it spoken aloud. 2 times 10 to the 96th kilograms pressed into a single cubic centimetre. That is, very roughly, the mass of 100 billion suns crushed into a space smaller than a sugar cube. At that density, according to one of the most serious attempts ever made to reach beneath the beginning of the universe, something happens that should be impossible. Gravity, the force that in all of ordinary experience only ever pulls, turns and pushes, the collapse halts. And in the span of a single Planck moment, the universe rebounds. This is the Big Bounce, the central claim of loop quantum cosmology. It proposes that the Big Bang was not the beginning of everything. It was a transition, a rebound from the dying body of a universe that came before ours. By the end of this video, you will understand exactly what the mathematics says happens in that last instant before the bounce. The modified Friedmann Equation that turns gravity repulsive, the critical density where it occurs, the physicists who derived it, and the competing models that arrive at a bounce by entirely different roads. You will also understand precisely what the bounce can explain, what it cannot, and the oldest question of all, which it quietly leaves untouched. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. To understand what loop quantum cosmology claims, you first have to understand what it is reaching toward, and why our two most successful theories of physics refuse to shake hands at the one place it matters most. General relativity, Einstein's theory of gravity, describes the universe at the largest scales. It treats space and time as a single smooth fabric, curved by mass and energy, and it works with a precision that borders on the absurd. Quantum mechanics describes the universe at the smallest scales, the world of particles and fields, and it too works with a precision that has never failed a single experiment. The trouble is that these two descriptions are written in incompatible languages. Where general relativity assumes a smooth, continuous space-time, quantum mechanics describes a world that is grainy, discrete, and uncertain. For most of the universe, this disagreement does not matter, because the scales never overlap. But there are two places where they collide head-on. One is the center of a black hole. The other is the beginning of the universe. At both, matter is crushed toward infinite density, and at both, general relativity does something no honest theory should do. It produces infinities. It breaks. Consider the equation at the heart of modern cosmology, the Friedmann Equation, written down by the Russian physicist Alexander Friedmann in 1922. In its classical form, it reads h squared equals 8 pi g over 3 times rho. Spoken plainly, the square of the expansion rate of the universe equals a constant, 8 pi times Newton's gravitational constant divided by 3, multiplied by the energy density of the universe. H is the expansion rate. G is Newton's constant, the strength of gravity. Rho is the density of everything the universe contains. The equation is simple, and it has been confirmed again and again. But run it backward in time, toward the beginning, and watch what happens. As the universe contracts as the scale factor shrinks towards zero, the density ρ climbs without limit. The equation says the density can simply diverge, climbing to infinity as the size of the universe goes to zero. That point of infinite density is the singularity, the Big Bang singularity. It is where the theory says space-time comes to an end and physics comes to a halt. The mainstream model of cosmology is the hot Big Bang, governed by the framework called lambda CDM, with an early burst of inflation. It accepts this singularity as the past boundary of everything. The singularity is the wall beyond which the equations cannot see. The standard model is extraordinarily successful. It predicts the abundance of the light elements, the structure of galaxies, and the temperature of the oldest light in the universe, the cosmic microwave background, measured at 2.725 Kelvin, just a few degrees above. Absolute zero to a precision of better than 1 part in 1,000. None of what follows challenges any of that. Loop quantum cosmology does not dispute the hot Big Bang. It asks a narrower and far more dangerous question. What happened at the singularity itself, the one place the standard model admits it cannot describe? Here the story turns to a reformulation of gravity that most people have never heard of. In 1986, the Indian-American physicist Abhay Ashtekar, working at what would become Penn State University, rewrote Einstein's general relativity in a new mathematical language. Instead of describing gravity purely through the curvature of a smooth metric, Ashtekar recast it in terms of a connection and a quantity related to the geometry of space, variables that now carry his name, Ashtekar variables. This was not a new theory of gravity. It was the same theory, dressed in different mathematics. But the new clothing made something possible that had not been possible before. It opened a path to applying the rules of quantum mechanics to space-time geometry itself. That path became loop quantum gravity, an attempt to describe space and time not as a smooth continuum, but as something woven from discrete, finite threads at the smallest scale. Loop quantum cosmology is the application of those techniques to the universe as a whole. It is what you get when you take the machinery of loop quantum gravity and aim it at a simplified, symmetric model of the cosmos, a universe assumed to be the same in every direction. It is, in the language of the field, a symmetry-reduced quantization. Hold that phrase. We will return to it, because it carries a weight that the popular accounts almost never mention. The first serious results came around 2001 from the German physicist Martin Bogerwald, also at Penn State. Bogerwald showed that when the geometry of space is treated quantum mechanically, the behavior near the classical singularity changes. The infinity that general relativity insisted upon was not, in this framework, inevitable. The equations could be continued through the point where the older theory simply stopped. This was the opening move. The full picture arrived in 2006, when Ashtekar, together with Tomasz Pawlowski and Parampreet Singh, published what is now called the Improved Dynamics of Loop Quantum Cosmology in Physical Review D and Physical Review Letters. They derived from the quantum theory an effective equation that describes how the universe evolves when quantum geometry effects are included. And that equation is where the entire story lives. It is the Friedmann equation again, but with one new term. In the loop quantum cosmology form, it reads h squared equals 8 pi g over 3 times rho times the quantity 1 minus rho over rho critical. Spoken plainly, the square of the expansion rate equals the same classical expression, the 8 pi g over 3 times the density, but now multiplied by 1 minus the ratio of the density to a critical density. Everything hangs on that final factor, 1 minus rho over rho critical. When the density rho is small, far below the critical value, that factor is almost exactly 1, and the equation collapses back into Friedmann's original. At everyday cosmic densities, loop quantum cosmology and standard cosmology are indistinguishable. This is why the framework does not disturb any existing observation. But as the density climbs toward the critical value, as the universe is crushed toward the regime where the older theory predicted a singularity, that factor shrinks towards zero. And when the density rho exactly equals the critical density, the entire right-hand side becomes zero. The expansion rate h becomes zero. The universe stops contracting. There is no smaller it can go. That is the bounce. What does it mean that a single added term, a single ratio, converts the end of time into a turning point? In the classical picture, if you plot the expansion rate against the density, you get an open curve that runs away to infinity, the runaway toward the singularity. In the loop quantum cosmology picture, that same plot closes into a bounded shape, an ellipse. The density is capped. It cannot exceed the critical value. The universe is forbidden by the quantum geometry of space itself from ever reaching infinite density. The singularity is not crossed. It is replaced. There is a second equation that completes the picture, and it tells you not just that the universe stops contracting, but the precise instant at which the reversal begins. It is the loop quantum cosmology form of the Réchaud-Dury equation, which governs acceleration rather than speed. Spoken plainly, the rate of change of the expansion rate equals minus 4 pi g times the sum of the density and the pressure multiplied by the quantity 1 minus 2 rho over rho critical. Look at that final factor, 1 minus 2 rho over rho critical. It does not become zero at the critical density. It becomes zero at half the critical density. What this means is subtle and important. The universe does not wait until the very floor of the bounce to feel the change. The acceleration flips sign earlier, when the density reaches half the critical value. The collapse is already being braked, already being turned before the universe reaches its densest instant. The bounce is not a wall the universe slams into. It is a turning that begins gently and completes violently. The deceleration setting in at half the critical density, and the full reversal arriving at the critical density itself. Think of a stone thrown straight upward. It does not stop at the top of its arc because it strikes something. It slows, halts, and reverses because a force has been acting on it the entire way up. The Ray-Chaudhuri equation is telling us that the contracting universe is like that stone in reverse. The repulsive influence begins to bite well before the turning point, so that the reversal, when it comes, is the completion of a process, not the shock of a collision. The mathematics describes a turning, not a crash. And where does the critical density itself come from? This is worth seeing, because the formula reveals something the popular accounts hide. The critical density equals the square root of 3 divided by 32 pi squared times the Barbero-Immerzi parameter cubed divided by Newton's constant times the Planck length squared. Do not be intimidated by the symbols. Attend to one feature. Buried inside that expression is the Planck length. And the Planck length is built from Planck's constant, the fundamental quantum of action. This means the critical density is a purely quantum quantity. If you imagine turning off quantum mechanics, letting Planck's constant shrink toward zero, as it effectively does at large scales, the critical density races toward infinity. And an infinite critical density means the bounce never happens. The cap rises out of reach, the density is free to diverge, and you recover exactly the old classical singularity. This is the mathematical fingerprint of the whole proposal. The bounce is not an add-on. It is what general relativity becomes when you refuse to let space be infinitely divisible. Take away the quantum, and the singularity returns. Restore the quantum, and the singularity is replaced by a flaw. So, what is this critical density, the ceiling that the universe cannot pass? In the improved dynamics, it comes out to approximately 0.41 times the Planck density. The Planck density is the natural unit of density built from the fundamental constants of nature: the speed of light, Planck's constant, and Newton's gravitational constant. And it is staggering. About 5.16 times 10 to the 96th kilograms per cubic meter. The critical density for the bounce, then, is roughly 2 times 10 to the 96th kilograms per cubic meter. Return to the number from the opening. That is the mass of something like 10 to the 20th suns, 100 billion of them compressed into a single cubic centimeter. This is not a density that exists anywhere in the present universe. The core of a neutron star, one of the densest objects we know, does not come remotely close. This is the density of the universe in the first sliver of an instant, the regime where, in the standard account, the equations simply end. There is a detail in this number worth pausing on, because it is the kind of detail the popular accounts leave out, and it foreshadows something we will examine much later. The exact value of that critical density depends on a quantity from the underlying theory of loop quantum gravity. That quantity is the area gap, the smallest possible non-zero area that space can have, which in turn is set by a dimensionless number called the Barbero-Immerzi parameter, with a value of about 0.237. In fact, the early papers in the field placed the bounce at a higher density, around 0.82 times the Planck density, using the lowest area eigenvalue. The value was later halved to about 0.41 when the more appropriate area gap, twice as large, was used. The number, in other words, rests on a choice about the fine structure of space. Keep that in mind. We will return to it. The mechanism behind the bounce has a name that sounds like a contradiction: repulsive gravity. As the density climbs toward roughly 1% of the Planck density, a quantum geometry effect begins to assert itself, a kind of pressure that has no counterpart in classical physics. It is not a force in the ordinary sense, not electromagnetism, not anything carried by a particle. It is a consequence of the discreteness of space itself, expressed through the mathematics of holonomies, a way of describing the curvature of space by tracking how a quantity changes when carried around a closed loop. This holonomy correction is what produces the extra term in the modified Friedmann equation. As the density approaches the critical value, this effect rises sharply, overwhelms the ordinary attraction of gravity, and reverses the collapse. Then, just as quickly, as the density falls away on the far side, the effect dies, and ordinary gravity resumes. The repulsion exists only in the most extreme instant, at the throat of the bounce, and nowhere else. By the time the universe has expanded to the conditions where inflation is thought to begin, the ratio of the density to the critical density has fallen to something like 10 to the minus 11. The quantum geometry effects are, by then, completely negligible. They do their work in a single moment and vanish. To grasp why discreteness produces this reversal, it helps to understand what loop quantum gravity claims space actually is. In ordinary physics, and in general relativity, space is a smooth continuum. You can divide a region in half, and half again, and again forever, with no smallest piece. Loop quantum gravity denies this. It proposes that space has a smallest possible grain, that area and volume come in discrete packets, that there is a smallest non-zero area a surface can have, called the area gap. Space, in this picture, is not a smooth sheet, but something closer to a fabric woven from finite threads. And below the scale of the weave, the question of how much smaller a region can be simply has no answer, because there is no smaller. Consider the difference between a photograph printed on glossy paper and the same image on a screen. From a distance, both look continuous, every gradient smooth. But bring your eye close to the screen and the illusion breaks. The image resolves into pixels, discrete squares of light, and there is no detail finer than a single pixel, because the pixel is the flaw of the picture. Loop quantum gravity proposes that space is the screen, not the photograph. At everyday scales, the grain is invisible, and space looks perfectly smooth. At the scale of the bounce, the grain is everything, and the curvature of that woven space is described mathematically through holonomies, a way of measuring how a quantity twists as it is carried around a closed loop in the fabric. It is the holonomy that cannot grow without limit, because the loops cannot shrink below the area gap. And it is that ceiling on curvature which, fed back into the equations, becomes the ceiling on density, the critical density, the flaw of the bounce. The repulsion is not a new force added to physics. It is the refusal of a pixelated space to be compressed past its own smallest pixel. The scales involved are difficult to hold in the mind, and they should be stated plainly. The Planck length, the natural quantum unit of distance, is about 1.6 times 10 to the minus 35 meters. To call it small understates the case to the point of absurdity. If you took a single atom and magnified it to the size of the entire observable universe, the Planck length, magnified by that same factor, would still be smaller than an atom. The Planck time, the unit of duration built from the same constants, is about 5 times 10 to the minus 44 seconds, the time it takes light, the fastest thing there is, to cross a single Planck length. The bounce in these models is not an event that unfolds over minutes or seconds. It is a transition measured in Planck times, in the smallest meaningful intervals the universe permits. The entire reversal, the halting of a collapsing cosmos and the ignition of an expanding one, happens in a window so brief that the word instant flatters it with too much duration. This is the part that stays with me from the opening physics. Not the violence of the densities, though they are beyond imagining. The restraint. At the most extreme condition the universe can reach, where the older theory predicted a tear in reality, this framework finds not a tear, but a rule, a smallest area, a capped curvature, a density that cannot be exceeded. The deepest place in physics on this account is not chaos. It is a boundary, observed. What this framework describes, then, is not a beginning, but a passage. On the far side of the bounce, before it, in the ordinary sense of the word, there is, in this picture, a prior universe. A universe that was expanding, then halted, then contracted, collapsing toward the density where its own collapse would be reversed. The bounce connects that contracting branch to our expanding one through what the physicists call a quantum bridge, a regime where the smooth language of space-time gives way to the discrete language of quantum geometry, and then re-emerges on the other side. We are, in this account, the expansion that followed someone else's collapse. This is the picture in its cleanest form, and it is worth stating who holds it and how confidently. Within the loop quantum cosmology community, the central result, that the simplest models bounce rather than break, is regarded as robust. It does not depend delicately on the exact initial state you feed into the equations. The effective description that gives the modified Friedmann equation has been checked against the full quantum evolution for sharply peaked states and found to track it remarkably well. And the resolution is not confined to the simplest, perfectly uniform model. In 2009, Ashtekar, together with Edward Wilson Ewing, extended the result to a class of models that allow for anisotropy, a universe that contracts at different rates in different directions, described by what is called the Bianchi-1 geometry. There too, in their analysis, the singularity is replaced by a bounce. These are real results, derived carefully, and they deserve to be presented as what they are, a serious, mathematically developed proposal for what replaces the singularity. But notice the careful wording running through all of it. The simplest models, the symmetry-reduced version, sharply peaked states. Each of these is a qualification, and each marks a boundary between what has been shown and what has been assumed. We are presenting, for now, only what the framework claims. We will test those claims in due course. For the moment, hold the central image firmly. A universe crushed toward a density beyond imagination. A single term in an equation turning gravity against itself. And a rebound that, if it is real, means our cosmos has a history older than its own beginning. The idea of a universe that cycles, that contracts and rebounds rather than beginning once and ending once, is older than loop quantum cosmology by nearly a century. It is worth tracing how the thought has moved through the minds that held it, because the history is also a record of the problems that have never gone away. It begins, fittingly, with the same man who gave us the equation. In 1922, Alexander Friedmann, deriving his equations from general relativity, noted that they permitted an oscillating universe, one that could expand, halt, and contract in turn. In 1931, Albert Einstein himself briefly entertained a cyclic model. But the deepest early objection came in 1934, from the American physicist Richard Tolman. Tolman studied what would happen to a closed universe that tried to bounce again and again, and he found a problem rooted in thermodynamics, in the behavior of entropy, the measure of disorder. In each cycle, entropy accumulates. The disorder of one cycle carries into the next. And Tolman showed that this build-up would make successive cycles grow larger and longer over time, which, run backward, means the cycles shrink toward the past. A naive, eternal cycle, in other words, cannot be truly eternal. The thermodynamics points to a beginning. Hold that result. It is not a detail of history. It is one of the three walls we will return to when we test what the bounce can actually claim. Half a century passed before the mathematics of quantum gravity gave the cyclic idea a new body. Ashtekar's variables came in 1986. Bojewald's singularity resolution arrived around 2001. The improved dynamics, with its critical density of 0.41 Planck densities, came in 2006. The anisotropic extension came in 2009. The same year, the European Space Agency launched the Planck satellite on the 14th of May to map the cosmic microwave background with a precision no instrument had achieved before. The convergence of dates is not a coincidence of the story. It is the reason the field became testable at all. For the first time, a quantum gravity proposal about the first instant could, in principle, be checked against the oldest light in the sky. Behind these dates are people, and their disagreements are as illuminating as their agreements. Consider Martin Bojewald, the founder of the Singularity Resolution Program. In 2007, Bojewald examined what could be known, even in principle, about the universe on the far side of the bounce. His conclusion was startling. Some properties of the prior universe, he argued, are washed out by the bounce. They leave so faint an imprint on our side that they are, in practice, undetermined. He called this cosmic forgetfulness. In his own words, it came as a big surprise that some properties of the universe before the Big Bang may have only such a weak influence on current observations that they are practically undetermined. The bounce in this view is a kind of amnesia. The universe that came before is not merely hidden behind the opacity of the early cosmos, it is, in deep respects, unknowable. Now hear the counter voice, because this is a live scientific dispute, not a settled doctrine. Alejandro Corricci and Parampreet Singh challenged Bojewald directly. They argued that for a universe like ours, the memory across the bounce is almost perfectly preserved, that the relative spread in the key quantities changes by less than 1 part in 10 to the 112th across the transition. Their reply carried a flat, declarative claim. There is no cosmic forgetfulness. Bojewald answered that their inequality did not constrain the pre-bounce fluctuations strongly enough to settle the question. The debate, cosmic forgetfulness against cosmic recall, remains open to this day. What does it mean that the founders of a field cannot agree on whether the universe remembers its own previous life? We will sit with that question, but not yet. There is another figure whose ideas press on the very meaning of the bounce. The Italian physicist Carlo Rovelli, a co-founder of loop quantum gravity. Rovelli has long argued that time itself may not be fundamental, that what we experience as the flow of time is emergent, a feature of how systems relate to one another rather than a basic ingredient of reality. This is his relational view of time, developed alongside his work on thermal time with the mathematician Alain Connes. Apply that idea to the bounce, and a strange thing happens to the word before. If time has no meaning at the throat of the bounce, where the smooth fabric of space-time dissolves into quantum geometry, then asking what happened before the bounce may be like asking what lies north of the North Pole. The question may dissolve. Notice this carefully. We will need it later when we examine what the framework is actually entitled to say about the deep past. Rovelli's reach extends further, into the other place where general relativity breaks. In 2014, Rovelli and Francesca Vidotto proposed that the same quantum geometry effect that halts the collapse of the universe could halt the collapse of a star inside a black hole. They called the result a Planck star. In their model, matter falling into a black hole does not crush into an infinite singularity. It reaches Planck density, where the repulsive quantum geometry pressure asserts itself, and the collapse halts. The black hole, in this picture, eventually tunnels into a white hole, its time reverse, an object that nothing can enter and from which matter emerges. Seen from outside, from our frame, this rebound takes an immense span of time, stretched almost beyond comprehension by gravitational time dilation near the horizon. Proposed as a possible resolution to the black hole information paradox and the so-called firewall problem, the Planck star is the bounce written small. The same mechanism, the same critical density, applied to a star instead of a cosmos. It is a topic worth exploring on its own, and we have followed the white hole side of it much further elsewhere. But hold the symmetry in mind. If the universe can bounce, perhaps every black hole carries a bounce inside it. There is no consensus on this among researchers of quantum gravity, and competing models of the black hole's fate exist. We present it as what it is, a serious proposal, not an established fact. This brings us to the competitors, because loop quantum cosmology is not the only framework that claims the universe bounces. To understand the strength of any one model, you have to see it standing beside the others that reach the same conclusion by different means. The most developed rival is the ekpyrotic or cyclic model, advanced by Paul Steinhardt and Neil Turok beginning in 2001 and 2002. Their proposal is rooted not in loop quantum gravity, but in string theory and its higher dimensions. In their account, our entire three-dimensional universe is a membrane, a brain, floating in a higher dimensional space. And the hot Big Bang was not an explosion from a point, but a collision between two such brains. The brains approach, collide, and rebound, and the energy of that collision is what we perceive as the beginning of the hot, dense phase. The Steinhardt-Turok model makes a distinctive prediction. It produces essentially no primordial gravitational waves, what physicists measure as the tensor-to-scalar ratio, near zero. And crucially, their flat universe cyclic model was explicitly engineered to handle Tolman's old entropy problem, by using a phase of accelerated expansion to dilute the entropy density before each contraction. Whether that engineering succeeds is a question we will examine. For now, mark the contrast. A bounce from colliding brains in extra dimensions set against a bounce from the repulsive quantum geometry of space. There is a third road taken by Roger Penrose. His conformal cyclic cosmology, proposed in 2006, makes the boldest claim of all. It holds that the infinitely distant future of one universe, when every black hole has evaporated and only radiation remains, can be mathematically rescaled and joined to the Big Bang of the next. Each cycle Penrose calls an eon. His model predicts faint concentric circles in the cosmic microwave background, the imprints of black holes colliding in the previous eon. Those predicted patterns have been searched for, and they remain observationally disputed. Penrose's framework, like the others, is a serious attempt by a serious mind, and, like the others, it has not been confirmed. 3 frameworks, 3 bounces. Loop quantum cosmology from quantum geometry, the ekpyrotic model from colliding brains, conformal cyclic cosmology from conformal rescaling. They disagree about the mechanism, they agree on the shape of the story, that ours is not the only universe in the sequence. And that very agreement should make us cautious rather than confident, because a conclusion that can be reached from 3 incompatible starting points may be telling us less about the universe than about something the human mind finds appealing. We will return to that suspicion. Now we come to the question that decides whether any of this is science or mathematics. Can the bounce be seen? Here, the honest answer is sobering, and it is the reason the foreshadowing in this video keeps gathering. The bounce itself is not directly observable. We cannot look at it. The earliest light we can detect, the cosmic microwave background, comes from the moment the universe became transparent, roughly 380,000 years after the hot phase began. Before that, the universe was an opaque fog. Everything earlier, including the bounce, sits behind that wall. The only conceivable messenger from before that wall would be primordial gravitational waves, ripples in space-time imprinted as a particular pattern in the polarization of the microwave background, called B modes. The hunt for those B modes is one of the great dramas of modern cosmology, and it carries a hard lesson. The announcement came on the 17th of March 2014 from the BICEP-2 collaboration operating a telescope at the South Pole. The claimed value of the tensor-to-scalar ratio was about 0.2, reported at a statistical significance that, on its face, looked overwhelming. For 12 weeks, it stood as perhaps the most important measurement in the history of cosmology. A direct image, it seemed, of gravitational waves from the universe's first instant. Then, confidence began to erode. By June of 2014, the team itself had softened its claim. And in January of 2015, a joint analysis combining the South Pole data with measurements from the Planck satellite delivered the verdict. The signal was contaminated by dust in our own galaxy, tiny grains aligned by magnetic fields mimicking the very polarization pattern the team had hunted. One of the researchers stated it without flinching. The dust is at least 40% of the signal, and it could be all of it. The detection evaporated. There is a discipline in that story worth pausing on, because it cuts against the cynical view of how science behaves. The error was not buried, it was hunted down, announced, and corrected by the very community that had the most to gain from the result being true. That is science working as it should. But notice the deeper lesson for our subject. The single clearest window onto the universe's beginning was thrown open, and what came through it turned out to be dust from our own backyard. The first instant remained hidden. What does it mean that our one direct line to the moment before the beginning has, so far, shown us only the foreground, our own galaxy's dust standing between us and the answer? The bounce, if it happened, has not yet let us see it. Today, the firmest measurements place the tensor-to-scalar ratio below about 0.032, a ceiling, not a detection. No primordial gravitational wave signal from the early universe has been confirmed. The next generation of instruments is being built to push the search further. The LightBird satellite, planned by Japan, with a goal of measuring that ratio to better than 1 part in 1,000. And the ground-based Simons Observatory rising in the Atacama Desert of Chile. A larger project called CMB Stage 4 has reportedly had its funding halted, leaving those two as the most sensitive efforts ahead. So what, concretely, would loop quantum cosmology predict for these instruments to find? This is where the framework earns its claim to be physics rather than philosophy. The proponents argue that the bounce leaves a specific fingerprint, a suppression of power at the largest angular scales of the cosmic microwave background. In 2020, Ashtekar, with Brajesh Gupta, Donghui Zhong and V. Srinath, published work arguing that Planck scale physics could alleviate certain tensions in the microwave background data, and that the universe must have expanded at least about 141 e-folds, 141 doublings upon doublings from the bounce until now. The framework predicts that the very largest features in the sky should show slightly less structure than the standard inflationary picture expects, along with related effects in the polarization. These are real quantitative predictions. They are also, so far, unconfirmed, and they sit at the largest scales, where the unavoidable statistical uncertainty of having only one sky to observe is greatest. Pause on that number. 141 e-folds. An e-fold is a single multiplication by the mathematical constant e, roughly a factor of 2.7. 141 of them, stacked one upon the next, is a magnification so vast it defeats ordinary comparison. Picture a single grain of sand and double its size, and double it again, and keep doubling. Long before you reached anything like 141 doublings, that grain would dwarf the observable universe many times over. That is the minimum expansion the framework says separates us from the bounce. Everything we can see, every galaxy in every direction, was, in this account, compressed into a patch unimaginably smaller than a proton at the moment of the rebound. The structures that became clusters and walls and voids were then the faintest quantum ripples, stretched across that staggering magnification into the architecture of the night sky. And here lies the cruelty of the observational problem. The signature the framework predicts is strongest at the very largest scales, the broadest features spanning the whole sky. But of those broadest features, the universe gives us only a handful of independent samples, because there is only one sky, and it is only so large. Imagine trying to determine whether a coin is fair when you are permitted only 3 or 4 flips total for the rest of time. A run of heads tells you almost nothing. The sample is too small to separate a real bias from. Ordinary luck. This is the predicament at the largest angular scales of the microwave background. The suppression of power that loop quantum cosmology predicts is exactly where the data is sparsest and the statistical noise, what cosmologists call cosmic variance, is loudest. It is possible that the bounce has already left its fingerprint on the sky, and that we will never be able to say with certainty that we are seeing it rather than chance. What does it mean that the one prediction which could confirm a universe before our own may lie permanently at the edge of what a single sky can prove? The framework may be right and unconfirmable at once. A true story we are forbidden, by the size of our evidence, to verify. That possibility, more than any equation, is the one I find myself returning to. And here, finally, the qualifications we have been holding begin to converge. The exact predictions depend on which version of the theory you use, and there is more than one. Different ways of handling the mathematics at the deepest level, called regularization schemes, with names like the improved scheme and the variants labelled MLQC1 and MLQC2, give different bounce densities and different predictions for the microwave background. In 2024, researchers worked explicitly on constraining these ambiguities using the microwave data, precisely because the ambiguities are real and unresolved. The framework, in other words, does not yet speak with one voice. It speaks with several, and they do not all say the same thing. It is worth being concrete about what that disagreement looks like, because it is easy to wave at ambiguities and move on, and the detail matters for honesty. The bounce, as we have described it, is most often discussed through what is called the effective description, a smooth, classical-looking set of equations that approximate the underlying quantum evolution. The modified Friedmann equation is part of that effective description. It is not the raw quantum theory. It is a translation of the quantum theory into the familiar language of expanding universe physics. The proponents have checked that this translation tracks the full quantum behavior closely, but only for certain well-behaved states, sharply peaked ones, the equivalent of a quantum universe whose properties are crisply defined rather than wildly spread out. The effective spacetime is an approximation, and, like every approximation, it has a domain where it holds and a frontier where it fails. Where exactly the classical description of a rebounding universe breaks down completely, and what replaces it there, remains an open technical question. Beneath that, there is genuine disagreement about how to do the quantization in the first place. There is the improved scheme, the standard form that gives the critical density of 0.41 Planck densities. But there are rivals, variants known by labels such as MLQC1 and MLQC2, and a construction due to Dapor and Legendre, and they do not all predict the same bounce density, nor the same imprint on the microwave background. Think of a translator working from a manuscript in a lost language. Several scholars produce several translations. All are careful, all are defensible, but they disagree on key passages, and there is no surviving original to settle the dispute. That is roughly the situation in the deepest layer of loop quantum cosmology. The disagreement is not a sign of carelessness. It is a sign that the theory has not yet been derived cleanly from its parent, loop quantum gravity, and so the bridge between them can be built in more than one way. In 2024, researchers were still actively working to constrain these competing schemes using the microwave data, which is precisely the behavior of a field whose foundations are not yet settled. There is a further difficulty with a name worth knowing: the trans-Planckian problem. The structures we see in the universe today, galaxies, clusters, the great cosmic web, are thought to have grown from tiny quantum fluctuations stretched to enormous size by the early expansion. But trace those fluctuations far enough back, through the bounce, and the relevant wavelengths shrink below the Planck length, into the regime where the very notion of a smooth fluctuation on a smooth background loses meaning. How to handle perturbations whose wavelengths dip beneath the grain of space is a problem the framework is still wrestling with. It is the kind of difficulty that does not announce itself in the headline version of the theory. And it is exactly the kind of difficulty that determines whether the headline version is true. Even the relationship between loop quantum cosmology and ordinary quantum cosmology carries unfinished business. An older approach, the Wheeler-DeWitt equation, attempted to write a wave function for the entire universe. And in that framework, famously, the variable for time drops out of the fundamental equation entirely, deepening the puzzle of how time emerges at all. Loop quantum cosmology inherits this lineage and this difficulty. When Carlo Rovelli says time may be emergent, he is not speaking loosely. He is pointing at a feature that runs through this whole family of theories. At the deepest level, the equations may not contain time as a basic ingredient, and the flow we experience may be something that crystallizes only later on one side of the bridge. What does it mean that our most fundamental description of the universe's beginning may not contain a when at all? We will let that question stand for now. It will matter when we ask what the word before can possibly mean at the bounce. These are not reasons to dismiss the framework. They are the texture of a living research program, presented honestly. A serious idea earns respect precisely by having difficulties this specific, this technical, this far from resolved. But they are also the reason the foreshadowing has been accumulating, paragraph by paragraph. Each qualification, the symmetry reduction, the sharply peaked states, the effective approximation, the competing schemes, the trans-Planckian frontier, the missing variable for time, is a place where what has been shown falls short of what is often claimed. We have kept faith with the material by laying every qualification on the table. Now those qualifications are about to do their work. We have now laid out the full architecture of the claim. The equation that turns gravity repulsive, the critical density and the quantum bridge, the history from Friedmann to Tolman to Ashtekar, the forgetfulness and the recall, the Planck stars, the colliding brains, the rescaled eons, the single window of primordial gravitational waves still dark, and the predictions, real but unconfirmed, resting on choices not yet settled. We have presented all of it as fairly as it can be presented, because a thing is only worth examining once it has been seen at its strongest. Now we examine it. For the past stretch of this video, I have presented what the proponents of loop quantum cosmology claim. I have given the framework its strongest formulation. I have not argued against a word of it. That was deliberate. Now we test whether the claims survive scrutiny. And to do that fairly, we must separate two very different kinds of statement that the popular accounts habitually blur together. The first kind is neutral physics, the modified Friedmann equation, the critical density, the repulsive quantum geometry effect, the prediction of suppressed power at large angular scales in the microwave background. These are mathematical and empirical claims about how a model behaves. They carry no hidden message about purpose or origin. A theist and an atheist can study the holonomy correction together and reach the same equation. There is nothing here to debunk, and I will not pretend otherwise. If loop quantum cosmology is someday confirmed, It will be a magnificent achievement of human reason, and it will sit comfortably within a created universe whose order we are slowly learning to read. The second kind of statement is different. It is the claim that rides on the physics like a passenger, dressed in the same clothes, hoping not to be checked. It is the claim that the bounce removes the need for a beginning. That because the universe rebounded rather than began, there is no longer any question of a first cause. No need for anything beyond the cycle itself. That claim is not physics. It is philosophy wearing the costume of physics. And it is the claim we will now examine. Let us state it in its strongest form, fairly. The proponents of bouncing cosmology argue as follows. General relativity predicted a beginning, a singularity, a wall beyond which nothing existed. Loop quantum cosmology dissolves that wall. The singularity is replaced by a bounce, and on the far side of the bounce, there is a prior universe. If there is always a prior universe, then there was never a first moment, never an absolute beginning, and therefore never any need for a cause that stands outside the chain. The universe, on this view, is self-sufficient. It needs no origin because it has no edge. That is the argument. Now we cross-examine it. And the first question is the simplest one a prosecutor ever asks. Does the evidence actually show what the witness claims it shows? Here is what loop quantum cosmology has actually demonstrated. It has shown, in simplified, highly symmetric models, a universe assumed uniform, or uniform with a single controlled kind of anisotropy, that a single bounce replaces the singularity. One bounce. A transition from one contracting branch to one expanding branch. That is a remarkable result. But notice the distance between what was shown and what was claimed. To get from one bounce to no beginning, you need not a single transition, but an infinite chain of them, stretching back without end. That infinite chain has never been demonstrated in any realistic model. It is not a result. It is an extrapolation, a hope projected backward past the one transition the mathematics can actually describe. What does it mean that a framework which proves a single bounce is so often spoken of as if it had proven an eternal cycle? It means the conclusion has outrun the evidence. And we need not take that on my authority. Listen to the architect of the framework himself. Abhay Ashtekar, describing how the theory handles the deep past, frames the result as setting the initial conditions for our expanding branch independently of what happens in the pre-Big Bang branch. Read that carefully. The framework does not determine the deep past. It brackets it. It hands you one bounce and declines to speak about the infinite regress behind it. The man who derived the equation does not claim what the popularizers claim on his behalf. This is the first failure of the argument, and it is a failure of logic, not of physics. A single bounce does not abolish a beginning. It relocates the question one step backward, to the contracting universe that preceded ours. And now the prosecutor asks the question the defense cannot escape. Where did that one come from? If the answer is another bounce, then where did the one before it come from? You are now standing inside one of the oldest arguments in human thought, and it is worth naming precisely because the physics has walked us straight into it. You cannot have an infinite chain of dependent causes. If every universe requires a prior universe to bounce from, and that one requires another, and so on without end, then the chain never actually gets started. And yet, here we are. The existence of this present moment is proof that the regress terminates somewhere, in something that did not itself require a prior cause. Something uncaused. Something that did not bounce from anything, because it simply is. The bounce does not remove this conclusion. It cannot. All it can do is add links to the chain, and a chain with more links still hangs from something. To answer the question of where the universe came from by pointing to a previous universe is not to answer it. It is to postpone it, and to hope no one notices that postponement is not explanation. There is a precise scientific result that sharpens this to a point, and it comes not from theology, but from cosmology itself. In 2003, Arvind Border, Alan Guth, and Alexander Vilenkin proved a theorem. It states that any universe which, on average, has been expanding throughout its history cannot be extended infinitely into the past. It must have a past boundary. The theorem is almost purely geometric. It does not care about the matter content, the energy fields, or the particular theory of gravity. It cares only about the average expansion along the paths through space-time. And its conclusion is that average expansion implies a beginning. Bouncing and cyclic models have been examined directly against this theorem, and extended versions of it have been applied to cyclic cosmologies, to Penrose's conformal cyclic cosmology, and to the Steinhardt-type models, finding in those cases the same past incompleteness. A bounce is not an automatic exemption. To escape the theorem at all, a cyclic model must be carefully engineered so that the expansion does not, on average, win out over the contraction. That is not a natural feature of a bouncing universe. It is a condition that must be imposed by hand precisely to avoid a beginning. And the model tuned specifically to avoid a beginning is not evidence against a beginning. It is evidence of how hard the beginning is to avoid. This is the inversion worth sitting with. The critics of design often accuse the theist of reaching for a god of the gaps, of inserting a creator wherever science has not yet filled in the picture. But watch what is happening here. To keep the universe beginningless, the cyclic model must invoke conditions for which there is no independent evidence, tuned for the express purpose of evading a result the mathematics keeps producing. What is that, if not a naturalism of the gaps? An unobserved mechanism inserted precisely where the evidence points the other way. The accusation, levelled honestly, lands on the accuser. Now we come to the second anti-theistic claim, and it brings back a name from the history we traced earlier. The claim is that an eternal cyclic universe requires no creation event, that the cycle has simply always been turning. We met the answer to this in 1934, long before loop quantum cosmology existed. Richard Tolman's entropy problem. In every cycle, entropy, disorder, accumulates and carries forward. The disorder does not reset. And so the cycles cannot have been turning forever, because an infinite past of accumulating entropy would have buried the present universe in a disorder it plainly does not have. Run the cycles backward, and they shrink. the entropy points inexorably toward a low entropy beginning. This is why the proponents of the most developed cyclic model, Steinhardt and Turok, had to engineer an escape, a phase of accelerated expansion to dilute the entropy density before each contraction. But examine what that move actually is. It is not a discovery that the entropy problem does not exist. It is a specific, model-dependent construction built for the sole purpose of escaping it. The problem is acknowledged, not dissolved. And recent work continues to investigate, as an open question, whether any cyclic cosmology can genuinely avoid unbounded entropy growth and the thermal death it implies. The honest status is that Tolman's wall, almost a century old, still stands. What does it mean that two independent results, a thermodynamic theorem from 1934 and a geometric theorem from 2003, both point to a past boundary, and that the leading bouncing models must be specially tuned to evade each of them? It means the beginning is not a relic of an outdated theory that the bounce has swept away. The beginning keeps reasserting itself through different branches of physics in every generation. You can push it back. You have not been shown how to remove it. The third claim is subtler, and it is the one that survives even if you grant everything the proponents want. Suppose, for the sake of argument, that the chain of bounces could somehow be made eternal. The defenders would say that then nothing needs creating, because something has always existed. But notice that this is not a defeat of the theistic position. It is a restatement of its starting premise. The theist has never claimed that nothing existed. The theist claims precisely that something has always existed, something eternal and uncaused. The only question that has ever mattered is what that eternal something is. And here the bounce offers no help at all, because the something it proposes, an eternal sequence of universes governed by exact quantum geometric law, is not raw, featureless matter. It is a system of breathtaking mathematical order. It runs on the modified Friedmann equation. It is governed by a critical density set to a specific value. It obeys a holonomy correction of a precise form. Unconscious matter does not write its own laws. To say the cycle has always existed is only to relocate the wonder, not to explain it. To push the question from why there is something rather than nothing, to why the something is so exquisitely, lawfully ordered. And that brings us to the precision itself, the fine structure of the bounce, and to the detail I asked you to hold near the beginning. The bounce occurs at a critical density of 0.41 Planck densities. But that number is not handed down from nowhere. It depends, as we noted, on the area gap of quantum geometry, which is fixed by the Barbero-Emerzi parameter, a dimensionless number of about 0.237. The critical density scales as the inverse cube of that parameter. Change the parameter slightly, and the critical density moves dramatically. Change it, and you change where the bounce happens, whether the subsequent universe inflates, whether it can produce structure at all. The very value that makes the framework work is a value that had to be what it is. The proponents will say, fairly, that this parameter is fixed independently by matching the counting of quantum states to the entropy of black holes. And that is a genuine, non-trivial consistency, not a free dial turned at random. I grant it fully. But step back and see what kind of universe this is. It is one in which a single dimensionless number ties together the entropy of black holes, the smallest possible area of space, and the density at which a cosmos rebounds rather than dies. What does it mean that the books balance like that? That a number measured in one corner of physics turns out to set the fate of the universe in another. A coincidence of that magnitude has a name in every human language, and the name is not luck. Consider the architecture of the argument the materialist must now defend. The bounce requires the right critical density. The right critical density requires the right area gap. The subsequent inflation, which the proponents argue becomes highly probable once traced through the bounce, requires the modified dynamics to hold. The whole structure must hang together, parameter locked to parameter, for a universe capable of containing minds to emerge on the far side. The defender of pure chance must say that all of this, the lawfulness, the tuning, the coherence, is simply how things happen to be, with no reason behind the reason. But it happened to be that way is not an explanation. It is the refusal to give one. When the equation requires a precise input, and the precise input requires another precise input, and the chain of precision runs deeper than anyone can see to the bottom of, the rational mind does not conclude that no decision was made. It concludes the opposite. Precision requires decision, and decision requires a decider, something with the power to set the constants, the knowledge of what those constants would produce, and the will to choose this configuration over the boundless alternatives. There is a way the materialist tries to escape this conclusion, and it is the most ambitious move in the entire debate, so we must give it a fair and full hearing. The move is the multiverse. And within the bouncing cosmology literature, it takes a specific and ingenious form. The physicist Lee Smolin proposed, beginning in the early 1990s, an idea he called cosmological natural selection. Recall the Planck star, the suggestion that a black hole, instead of crushing matter into a singularity, bounces it through to a new region of space-time. Smolin took that idea and ran with it. Suppose, he said, that every black hole gives birth to a new universe on its far side, a baby universe. And suppose that each baby is born with physical constants slightly different from its parents, slightly mutated. Then universes whose constants happen to produce many black holes would produce many offspring, and those offspring would inherit black hole-friendly constants. And over countless generations, the population of universes would come to be dominated by those finely tuned for making black holes. Fine-tuning on this view is not a decision. It is the output of a Darwinian process, running across a lineage of universes, selecting for fertility the way biological evolution selects for it on Earth. It is, one has to admit, a beautiful idea. It is fully naturalistic, and it even makes a prediction. Our universe's constants should be very near the values that maximize black hole production. Now let us examine it. The first thing to notice is that not a single one of these other universes has been observed. Not the parent, not the siblings, not the offspring. The entire population exists only in the mathematics. The mechanism that supposedly generates them, the tunneling of a black hole's interior into a new, expanding cosmos with mutated constants, has never been demonstrated. It is a conjecture layered upon the conjecture of the Planck star, which is itself an unconfirmed application of the unconfirmed bounce. We are now 3 speculative stories above the ground floor of confirmed physics, and the staircase is made of mathematics alone. And the prediction that was meant to make it scientific has been challenged on its own terms. Alexander Valenkin argued that raising the value of the cosmological constant would actually increase black hole formation, which, if correct, means our universe's constants are not the black hole maximizing ones the theory requires, and the conjecture fails its own test. The matter is contested. But notice that even the defense of the idea now depends on disputed calculations about universes we cannot see. Here is the inversion that exposes the whole maneuver. The multiverse, in every form, is proposed for one reason: to explain away fine-tuning without a fine-tuner. If you have an unlimited supply of universes with random constants, then of course at least one of them will, by chance, have the values that permit observers, and of course we find ourselves in that one because we could not find ourselves anywhere else. The fine-tuning dissolves into a selection effect. But ask what has actually been purchased with this move, and at what price? To avoid concluding that one universe was designed, the materialist posits an infinity of universes for which there is no evidence, generated by a mechanism that has never been observed, governed by meta-laws that determine how constants mutate and how universes reproduce. Meta-laws which are themselves a deeper layer of unexplained order. The fine-tuning has not been removed. It has been relocated and multiplied. You were asked to explain the precision of one universe. You have answered with the unexplained precision of the machine that stamps out universes by the billion. This is not the elimination of design. It is design pushed up one floor and left unaddressed, while the bill for an infinity of invisible worlds is quietly slipped under the door. Before I continue, consider what is being asked of you here. Take a moment with it. You are asked to believe in an unbounded ensemble of universes, none of them ever detected, rather than accept the one conclusion the visible evidence keeps pointing toward. Ask yourself honestly, which of those is the larger act of faith, and which is the more economical reading of the data in front of you? By the ordinary standards scientists apply everywhere else, prefer the explanation that posits fewer unobserved entities. Prefer the hypothesis that can be tested. The multiverse fares badly, and the inference to a single intelligent cause fares well. The conclusion is not being forced by religious conviction. It is being resisted by it, by a prior commitment to keep mind out of the explanation at any cost, including the cost of an infinity of ghosts. There remains one last line of defense, and it is the one most often deployed when the others fail. It is the appeal to the future. We do not understand the bounce fully yet, the defender says, but science will eventually explain it. And when it does, the need for any cause beyond physics will vanish. We must examine this move directly, because it sounds like patience, and it is actually faith. Recall the honest state of the field, stated plainly by its own practitioners. Loop quantum cosmology is, in the words of one reviewer, the symmetry-reduced version of the full theory, and it should be underlined, that same reviewer wrote, that the derivation of the cosmology from the full theory of quantum gravity is not yet fully demonstrated. The framework has not been derived from its own parent theory. Its central claim, the bounce, has never been observed. Its predictions depend on a choice of regularization scheme that remains unsettled, with rival versions giving rival answers. This is not a finished science with one gap left to close. It is an active, unfinished research program. To point at that unfinished program and promise that it will one day eliminate the need for a cause is not a scientific statement. It is a prediction about discoveries that have not been made, offered as though the discoveries were already in hand. And here the materialist faces the question that cannot be answered by any future telescope, because it is not a question physics is equipped to ask. Suppose loop quantum cosmology is confirmed tomorrow in every detail. Suppose the microwave background reveals exactly the suppression of power the proponents predict. Suppose the bounce is, beyond doubt, real. You would have explained how the universe rebounded. You would not have explained why there is a universe to rebound at all, why there is something rather than nothing, why there are laws rather than chaos, why those laws take the one precise form that permits a cosmos to exist and minds to notice it. Science describes how the universe operates. It cannot, by its own method, reach behind existence to explain why anything is there to operate. That is not a temporary gap awaiting a future paper. It is a permanent boundary of the method itself. The equations, however deep, describe the dance. They are silent on why there is a dance, or a floor to dance upon, or anything at all. Press on that silence because it is the heart of the matter. Imagine you could subtract everything the bounce gives you. No prior universe, no contracting branch, no quantum geometry, no area gap, no critical density, no space for it to live in, no time for it to happen in, no law to govern it. Absolute nothing. Not empty space, for empty space is already something, a stage with dimensions and fields. True nothing. No stage, no actors, no script. Now ask the question honestly. From that, nothing could arise. Nothing has no causal power. It has no potential, because potential is already a kind of something. Zero added to zero is zero, however long you wait, because there is no waiting and no you and no clock to wait against. If there had ever been true nothing, there would be nothing still. And yet, there is a universe, bouncing perhaps, but indisputably here. The only conclusion that survives is that something has always existed, something that did not come from nothing because it never needed to, something uncaused and eternal. The bounce does not contradict this, it illustrates it. Every version of the story, cyclic or not, eternal or not, ends at the same door. An eternal something, behind the something we can see. And the question the equations cannot touch is the only question that finally counts. Is that eternal something blind, or does it see? This is the part that stays with me. Not the scale of the densities, staggering as they are. The order. A universe crushed to 10 to the 96th kilograms in a cubic centimeter. And even there, at the most violent instant imaginable, it does not descend into formlessness. It obeys an equation. It honors a critical density. It rebounds according to law. The deeper physics looks beneath the beginning, the more law it finds, never less. And law is not the signature of accident. Law is the signature of a mind. So let us render the verdict on the claims we set out to test. The claim that the bounce removes the need for a beginning fails. It proves a single transition and smuggles in an eternity it has not earned. And two independent theorems, thermodynamic and geometric, keep forcing the beginning back into view. The claim that an eternal cycle needs no creator fails. It does not escape the conclusion that something has always existed. It merely insists, without warrant, that the eternal something is unconscious, even as the framework reveals that something to be a structure of extraordinary mathematical order. And the claim that science will someday explain existence itself fails, not because science is weak, but because the question of why there is anything at all lies outside what any physics can reach. None of these failures touch the equations. Every one of them touches the philosophy that tried to ride the equations out of the reach of the oldest question. The physics is welcome to stay. The smuggled conclusion is not. Let me bring this exploration to a close. We began with a number at the edge of physics, 2 times 10 to the 96th kilograms in a cubic centimeter, and a single term in the Friedmann equation, 1 minus rho over rho critical, that turns gravity against itself and converts the end of time into a turning point. We followed the big bounce of loop quantum cosmology from Friedmann's first equations and Tolman's entropy problem, through Ashtekar's variables and Bojewald's singularity resolution, to the improved dynamics and its critical density of 0.41 Planck densities. We stood at the quantum bridge, where one universe is said to become another. We heard the founders argue over whether the cosmos remembers its previous life. Cosmic forgetfulness against cosmic recall. We watched the Planck star carry the same bounce into the heart of a black hole. We set the framework beside its rivals, the colliding brains and the rescaled eons. And we found the single window onto the first instant. The primordial gravitational waves, still dark, the predictions real, the confirmation absent. Deepest version of the theory not yet derived from its own foundations. And when we tested the one claim that reached beyond the physics, the claim that the bounce abolishes the need for a beginning, we found it could not bear the weight. The bounce proves a single transition, not an eternity. The thermodynamic theorem of 1934 and the geometric theorem of 2003 keep forcing a past boundary back into view, and the models that escape them must be tuned by hand for the express purpose of escaping. And even an eternal cycle, granted for free, would not give the materialist what he wants. It would only confirm what the theist said first, that something has always existed, while leaving unexplained why that something is a structure of such precise and lawful order. The deeper we looked beneath the beginning, the more law we found, never less. And law is not what accident leaves behind. The evidence, examined honestly, points in one direction. Behind the modified Friedmann equation stands the order it expresses. Behind the critical density stands the precision that set it. Behind the bounce, if the bounce is real, stands the same question it was invented to escape. And the answer it keeps circling back toward is not unconscious matter, blindly turning, but an eternal, uncaused cause, possessed of power enough to set the constants, knowledge enough to know what they would build, and will enough to choose this universe over the silence of nothing. The bounce did not remove the creator from the story. It only showed us one more layer of the craftsmanship. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. There is a thread we touched only in passing tonight, and it may have stayed with you. If the universe can bounce, if matter crushed to Planck density rebounds instead of vanishing, then what happens inside a black hole, where matter is crushed the same way? The Planck star, the black hole that tunnels into a white hole, opens a door we barely cracked here. I have followed that door much further. You will find where on the end screen now and in the description below. The bounce offers us a universe without a first edge, and then, in the fine print of its own equations, hands the oldest question back to us unanswered. Not what banged, not even what bounced, but why there is anything here to rebound at all. Good night.